And thank you everyone for attending today's webinar. We're going to be covering Nastran What's Next. And with Nastran being more used out in industries and out in the fields, a lot of questions get filtered back to us of, okay, we've got our results, now what? And that's kind of the path we're going to go down today. Before we get going too far, I'd just like to show this slide, make sure everybody can hear me. And again, you can plug in some questions in there and Dan will field those during the webinar. And as Ashley mentioned, we'll have dedicated time at the end of the webinar to address those questions or any of them that Dan might save for the end. Real quick, a brief about Hagerman and Company for anyone who might not be very familiar with us. As you can see by the map, we are heavily centralized in the middle of the US basically, but we've got offices from coast to coast. Our field technical staff, which is people like myself and Dan, combined, we have well over 175 years of experience in the engineering and implementation field. We've also got 30 years of software sales and implementation, especially on the data management side for products like Autodesk Vault. Okay, so if you already have Nastran, you're probably decently aware of what all you can do, but let's go ahead and break through some of these and give you a more expanded view of what you can do. And this is not even a complete list. So obviously linear statics is a very common analysis to run, but we also have buckling and normal mode analysis. We've got pre-stress static and normal mode analysis. There's also linear steady state heat transfer. Now, anytime you see heat mentioned with Nastran, I want to be clear that Nastran is not calculating the generation of heat. Heat is typically a low variable that you need to know going into the analysis. What it will calculate is how that heat propagates through the system or through the pieces, I should say, and how those heat calculations might impact the stress of the material. As we know, if you heat certain materials up, really all materials, it affects the stress either in a positive light or a negative light, depending on the heat properties and the heat situation. So anytime you see the heat, that's what it's actually doing. We can also work with composite materials, so layered materials come into play. We have assembly modeling and assembly contacts. Thermal stresses, again, how is that temperature affecting thermal or affecting the stress of the components? We've got nonlinear statics, so that's something we're actually going to touch on today very briefly. Nonlinear transient heat transfer, so again, another heat situation, but this time a time variable comes into play. We also can perform nonlinear steady state heat transfers, as well as frequency response, random response, linear and nonlinear time dependent responses. We can work with advanced nonlinear materials such as hyperelastic and polymer materials. And there's impact and drop testing available in Nastran. So I just wanted to cover, make sure everybody was well aware of the bulk of what Nastran can do. There's a few more that's not mentioned here, but that's a good, well-rounded picture of it. Let's talk about the initial FEA process. This comes up quite often. We cover this during our training class. You start with your geometry, you bring it into Nastran, and that geometry, it can be obviously native Inventor, but it could also be imported geometry like a step file or a sat file or something like that. Excuse me. And once you bring it into Nastran, if you have not assigned the material in Inventor, you can assign a material in Nastran. You're going to create your mesh, apply your boundary conditions, that's your loads and constraints, and run your analysis and look over the results. And the biggest question we get is, okay, I've got my results. Now what? And that's what we're going to cover today, because a lot of users don't realize once you have your results, you're not done. You just got started. So let's look at what goes into that process of getting started. That carries us into our first demo. There's actually going to be 2 demo segments in today's presentation. I'll bounce out of the PowerPoint into the demo, then I'll come back into the PowerPoint once the first demo is done and go into the second demo a little bit later. So again, I want to give a brief overview for those not aware. Maybe you're attending this thinking, okay, what is Nastran and how can it help us? There is another webinar that Hagerman did not too long ago that is a nice introduction. But again, I want to walk everybody through some of the steps of how to get to Nastran, where it's located, and some of the things you're going to need to do your analysis. So looking at my model, this is a native Inventor model. I'm going to go into Nastran by clicking on the Environments ribbon tab. And you'll notice there's an Autodesk Inventor Nastran icon. There's also a stress analysis icon. This is a separate FEA engine from the Nastran engine. The stress analysis icon is what we've had in Inventor Pro for many, many releases, long before we ever incorporated Nastran. The Inventor Pro stress analysis is limited to static only and normal mode analysis only. It can do parts and assemblies, but it is limited to those 2 types of analysis test. Whereas Nastran is not. We can go into nonlinear and other frequency analysis modes. So when I click on the Nastran icon, you'll notice I never leave Inventor. It takes me into a sub-environment in Inventor. I still have access to all of my familiar Inventor ribbon tabs, and I can quickly get out of Nastran, make a model change, and come back in here, and the results are, or the updates are there. I don't have to run any kind of re-import or anything like that. Now, I've already got this analysis that I've ran before, but I'm going to start over. So I'm just going to make a new analysis. Let's go with that one. And the units, I'll go ahead and select English units. And it's going to be a linear static. Now, if you've never ran any analysis before in Nastran, as soon as you come in here the first time, it defaults to a linear static analysis type. Okay, so now I've got analysis 1, that's the one that was already there, and analysis 2 is the new one that I created. So let's set some things up in this model. I'm going to set up the material property, so I'm going to work with an idealization. It's going to be a solid idealization. So this basically tells Nastran what type of elements are we going to be breaking this down into. It's either going to be a solid or a shell, so this would apply to surface models, or it's going to be a line element. This would apply to anything coming out of the frame generator, pretty much. Any kind of beam analysis, framing type analysis would work. For this one, we are going to use the solid element analysis. The material does pull from what's in Inventor. So if you have that material already configured, it's going to be there. If not, of course, you can pull up the material library and select any of the materials here, or even load your own custom database. Again, I'm going to be working with what's there. It's a mild steel, and I'll simply change the color of the mesh. The next step, are you working with any connectors? In this particular example, we're not. There's various types of connectors, from bolt connectors to rod connectors, cable connectors. We're not working with any surfaces, so there's no offset surfacing to come into play. There's no structural members. So the next step is looking at the boundary conditions. So I'm going to apply a constraint to the central bore diameter of this. It is going to be a grounded constraint. So it's going to be a completely fixed constraint. All directions are locked down. And I'm simply going to change the color of the preview arrows. This is personal preference, absolutely not required, but it does help to visualize what's going on. Now I'm ready to apply some loading to this particular model. So on the top 2 forks, I'm going to apply a load in the negative Y direction. And you'll notice I'm using the part coordinate system, so it correlates to the graphic down here, the coordinate system icon down in the lower left. So for this, it's going to be in the negative Y, and I'll say negative 200 pounds of force. Now I've got some options here. I could either put 200 pounds on each fork, or I can say, you know what, that's a total force. So 2 forks is 200 pounds each one, is going to get 100 pounds. So whatever value you plug in here using that total force, it will split that value amongst all the selected or affected surfaces. Again, I'm going to change a color here, personal preference, not required, but visually it lets you know, are you going in the right direction? Because if I had not put in that negative and left it as just 200, then it would be applying the load in the wrong direction. I took out the 2, didn't I? So it'd be going the wrong way. So for this, I'll say negative 200. It's going the proper way. I'll say okay. And I'm going to put another load on the bottom. Similar workflow, selecting the 2 inside diameters of the forks. It's going to be a total force. This time it's going to be in the negative X direction of 100 pounds. And again, just turning on the preview arrows to make sure I've got the right direction applied. Now we're going to look at applying a mesh. And when you go into Nastran, the mesh is going to be kind of a recommended or calculated, if you will. And it's based on some basic rules for meshing. It gives you a value of that mesh based on your CAD units or your simulation units. This time we're looking at inches, but if we were in millimeters, it would be in millimeters. And you can make this mesh size either more coarse or more fine. You don't have to use what's here. What I typically advise is take whatever the recommendation is and go just a little bit more coarse, not a lot. So in this particular case, it calculates a recommended of about 0.186 inches. So I'll just say 0.2. So just a tiny bit more coarse, not too much. Go ahead and generate that mesh. And what you want to look for in a mesh is good, consistent pattern distribution and sizing. Now the sizing is going to fluctuate a little bit about when you go into smaller faces or round bore diameters, you'll see the mesh actually reduce in size. On a larger face, it'll get bigger in size. But what you want to look for doesn't really come up too much with a native Inventor model. But if you're working on something that's an imported step file or coming from another CAD format, it can happen. You can have in the middle of nowhere a sudden concentration of the mesh changing size and changing quantity. That typically indicates some kind of topology issue with that surface. And again, it mostly happens on imported components if it's going to happen at all. If you see something like that, you definitely want to address that before you go any further. So watch out for things like that when you're importing from McMaster-Carr or Grainger. With how those files are translated out of the native CAD product, they can translate negatively into Inventor, and you've got to address that. So I've got my mesh, looks pretty good. I'm ready to just run my first analysis. Doesn't take very long. Again, it's a linear static. It's a pretty quick analysis. When it's done, Nastran gives me a prompt, says the analysis completed. So I say okay, and I can go look at the results. Now, with this particular weather map that shows up, a lot of people want to step into this and say, okay, it's red down there at the bottom of the forks. That means it's going to break. Yeah, no. Red does not always equal bad or break location or failure location is what I should say. Red simply indicates the worst case depending on the test you're looking at. And the weather map will change color transitions. You go to a different type of analysis, the colors will actually invert. So at this particular location, it's showing me that the von Mises stress plot is about 11,000 PSI. That's a little small, so let's make it a little bit bigger where everybody can see. And let's reduce the number of bars. Okay, so we're looking at about 11,000 PSI for the max stress. Does that mean it's going to fail at that location? No, not necessarily, because you have to take these numbers and go back to the material specs. That's where all of this is based at. Now we can look at other types of result plots. We've got the von Mises as the default. We can look at the displacement to see how much those top two forks are moving. And again, it looks like they're moving about 0.02 of an inch or 20 thousandths, if I'm doing that math right in my head. Not moving a lot, so we're probably okay. We can look at the safety factor, and again, this is where the colors will inverse. You'll see them flip, and the red in this case indicates the lowest safety factor. So we're looking at about a 3.5 safety factor. Not bad. Just based on that number alone, again, it goes back to the material properties. That tells me this is probably okay, but what does that really mean? That's the next slide. So it'll work, right? No. One test is not enough to tell you anything. You get an idea of what's happening, but you don't have a complete picture yet. There's a lot more work that you've got to do after you run that first test. Think of the first test as kind of a sanity check. You want to look at it to say, okay, is it stressing where it should be stressing? Is it moving in the direction it should be moving? There's a lot of checks and balances that you have to do to know if you're going down the right path. So Weather Map 101, again, red does not always equal failure. It simply indicates the highest or lowest calculated value. Look at how your weatherman uses those radar maps, those temperature maps. That red moves as we go through the season. You know, the 105 degrees red in the summer, well, we get into the dead of winter and 45 degrees becomes red. It's all relative to everything else around it. Same thing applies here. The values are compared back to the material properties. So the values you see broke down in the tree go back to the material properties and relate to that. The stress amount, you know, if it's 7,000 psi, okay, what is the yield point of our material? That's something you've got to know when you get these results, and you compare it back to that. If the yield point of the material is 5,000 psi, okay, our calculation of 7,000, it's going to break. Where? We don't know, but it's not going to withstand that much pressure. The calculations, again, they can change each time you run the simulation. You could run it, go to lunch, come back, rerun it again, and they can change just a tiny amount. And it's all based on how each node element is calculated when the analysis runs. There's no set order that it goes from element 1 to 2 to 3 to 4. It doesn't work that way. The colors will shift spectrum, again, depending on the test. So where red on a von Mises will show the highest stress, red on a safety factor will show the lowest safety. So that's why I say it can show the highest or the lowest depending on the test you're looking at. The graph is customizable, as you saw. You can tweak the levels, you can tweak the quantity, the size of the text. For that matter, you can even set it relative to the actual values for the material, because what you're seeing show up on the graph are calculated based on minimum calculated stress and maximum calculated stress. And then large displacements, are they coming into play? That's another big question you have to ask yourself. When you get these results, is there any large displacement amount? And I cannot give you a magic number that says above this amount is a large displacement, below this amount is not. It doesn't work that way either. It's relative back to the overall size of your component. That's something we're going to look at here briefly. So you got your first results. Where do you go? You know, we're at the proverbial fork in the road. First run results, we either refine the mesh and repost and reprocess and rerun that analysis, or we go build a prototype, see how that does, and go to manufacturing. Ultimately, what are we trying to do? We're trying to use Nastran to predict what's going to happen with this design, so that when we get to a certain point of confidence, we only have to make one prototype to verify the results. You don't want to have to build 15, 20, 30 prototypes. That's super expensive. So initially, you're going to tweak Nastran as you're learning it and adjusting. You're going to tweak it to where the results that Nastran are giving you match what you've already seen for products out in the field, match the expected results. Once you have that, then you've got the confidence on designing new products, and you can use Nastran to run those calculations, get confidence there, and build one prototype before you go to manufacture. That's the whole goal of all this, to reduce the number of prototypes. By the way, if anybody's looking for a good stable structure, the letter M seems to be able to withstand tremendous amounts of stress. All right, so the next situation we're going to look at, well, actually, let me go back to this one. Let me go back here. On this particular situation, we're going to refine the mesh. And with that mesh, we've got our default that we set it to, the 0.2. This is a global mesh size. When you reduce this, you want to take very small baby steps. So we started at 0.2, let's go to 0.18. Regenerate your mesh and rerun your results. So now when I rerun this, what you're going to do with each one of these tests is you're going to log the results. So the first test, we started out 11,000 something, I think is what it was. I'm going off of memory, so I'll say 11,500. And you're going to graph those results because you're looking for convergence of the results. You're looking for where these numbers get to where they're not changing. As you're making mesh adjustments, you want these numbers to start flatlining, if you will. So this one is 12,171. We'll just plug it in. Okay, so there's a global mesh of 0.18. Let's do another one. We'll say 0.15. Regenerate that one and rerun that test as well. We're not changing the loads. We're not changing the constraints. The only thing we're doing is refining that mesh. And working with mesh adjustments can sometimes be a game of cat and mouse, if you will. You've got to be careful working with them, because if you make it too fine, sometimes you can actually make a stress riser where stress may not actually exist. So again, we've got a third number here, looking at 12,154. All right, so it didn't change much from that second test. And what you may notice is the stress area, the highest amount, might move around a little bit, might float from one fork to the other. It may move up and down a little bit, but it's staying in the same basic neighborhood. And that's what you want to see. You don't want to see that stress suddenly shoot out here to an area that shouldn't be under stress. When that happens, go back to your calculations and your setup. Something is off somewhere. So in this situation, our stress is staying in the same neighborhood. I think the first one is actually over here on the right-hand fork. Now it's moved over to the left-hand. So we've been making some global mesh refinements. I might go one more, maybe. Let's see, we'll say 0.12. Okay on that one, and rerun that last one. That got pretty small. Now, as you make your global mesh size smaller and smaller, it will take those tests longer to compute. So there's one trade-off, is time. So be careful making them too small right out the gate. It can take a very long time to run that calculation. So now we're looking at about 12,824. All right, so it jumped up a little bit. I might look at that and say, okay, there could be an outlier. It could be getting some stress where stress is not actually coming into play. So I might back it off a little bit. We went from 1.5 to 1.2. I might go say 1.3 or 1.4. But the other thing I'll do is instead of a global refinement, I'll do a local mesh control. So let me run this one real quick and plug in those numbers. With the local mesh control, you're able to refine areas of the model to a smaller mesh calculation, and you're saving time and efficiency doing that. So now we're 12,408, say 12,483, not 14, 12,483. Yeah, I brought it down a little bit more. All right, so now we're going to look at a local mesh control. So I'm going to invoke the mesh control, and you can either do it based on the vertex data, so that's the vertex where each one of the elements meet, or you can base it off of face input. Face tends to be a little bit more user-friendly to work with, in my opinion. So I'm just going to select all of the faces that seem to be affected by that stress. I'll get them on both sides here, and that should be good enough. So we're hovering at a global of about 0.14, so I'll take this down to 0.12, regenerate my mesh, and then rerun the results. And you'll notice that it runs a little bit faster than it did a minute ago with a 0.12 on the global, because that global is applying to everything. This one is only applying to the affected faces. So it does give you the results a little bit faster. So we're looking at about 12,048. Come down a little bit. All right, so we'll do one more mesh control, and we'll say down to maybe 0.1. Refresh that mesh and rerun. The ultimate goal is as you refine the mesh, you want to see these results change very little. So you want to see this start to trend out to a flat line, or as close as possible as you can get. Now, if it suddenly spikes up, okay, then you've probably got an outlier calculation. That's possible. So we'll say 170.86. And I could probably look at this and say, okay, results have converged. This guy right here could be an outlier. I could go back and rerun the numbers, maybe do some lesser amount tweaks. But ultimately, what you're looking for, a good example of some numbers, is something like this, where it actually starts to flatten out, and no matter how much refinement you make, the results don't really change much. That gives you some confidence that what you've got configured is giving you some good, accurate results. Now, back to this situation, that's comparing the stresses. What about the deformation? That's where that large deformation can come into play. So in this particular situation, we're looking at a flat-walled tank, and what you're actually looking at, this gray area here would be the inside of the tank, and this would be the center line. So you're looking at a quarter of a square tank. And we set up some various boundary conditions on this. So I'm gonna walk you through this real quick. On the linear static, what we've done, we do this on the linear static and the nonlinear static that we're going to run in a moment. Instead of using it as a solid element, we configure it as a shell, and we apply a thickness for that material because it's going to be a sheet metal tank, most likely. It's going to be made out of stainless steel, and we have all of these outside faces selected. You'll notice I do not have what I termed as the interior of the tank. I don't have any of those plain faces selected, if you will. So there's the material setup. We also have a load setup, which is a pressure. And this is not just a pressure load, a one value pressure load. It's actually a variable load. So we're starting out with a zero pressure at the top. And as we get to the bottom, this is an 8-foot tall tank. I think it's 8 feet, 7 feet or 8 feet, one of the two. As we get to the bottom of it, we're calculating that pressure to be about 4 psi. It actually comes in the neighborhood of 3.7. So I just said 4. Let's give ourselves a little bit of a pad. So 4 psi at the bottom. And you'll notice the arrows actually indicate a change in the load. That's the yellow arrows that you're seeing. So they'll start out non-existent at the top, and as you get closer to the bottom, those arrows increase in size, and of course we've got even distribution along the bottom face as well. As for constraints, we've got a couple of symmetry constraints set up on this. So for this one, because this is a symmetrical design, we can use the X, Y, or Z symmetry options. So in this example, we've got an X-axis symmetry. So what that actually plays into, the X-axis symmetry, oops, I accidentally deselected that, so let me try that again. So the X-axis symmetry is playing on that green line that you see, and it keeps that edge and that bottom edge from moving left to right relative to the X-axis down here in the lower left. And then we've got a Z-axis symmetry on the other set of edges, and same thing, it's keeping them moving left to right based on that Z-axis. What it does allow is it allows the flexing in and out on both of those directions. So while the edges will maintain their position, the tank will be able to bulge in that area from the pressure. And then we've got a Y-axis constraint on the bottom. Basically, this tank is going to be setting on the ground, and we're going to assume that the ground is never going to be moved. So we've got a complete Y-axis fix location on that. Now, when I run this, again, it's a linear static. The mesh is a linear mesh. It gave me a suggested size. I made it just a little bit more coarse. Again, this is going to be kind of my first run of this. And I'll look at the stresses. In a situation like this, a lot of times I won't pay too much attention to the value of the stress. I'll look at the location. Is it stressing where it should be? Is it stressing in the direction it should be stressing? But something like this, especially on thin-walled parts, I'll look at displacement. What is my displacement showing? It's showing, and again, let me enlarge this so we can see a little bit better. The displacement is 10 inches, almost 11 inches on an 8-foot tall tank. That's a lot. Now, that's why I say I can't give you a magical number that says above this is large, below that is not. It's relative to the footprint of the product or the system that you're working with. 11 inches of displacement on a 7 or 8 foot tall tank, that's big. So in my book, that says large displacement, something off is going on somewhere. We need to take this out of a linear static and go into a non-linear static. Here's where Nastran saves you a ton of time. I've got analysis 1, everything is configured. All I've got to do is right click on it and duplicate it. When I do that, it recreates everything. I've got my shell idealization, I've got my material associated with it, I've got my loads already applied, all of my constraints are applied, my mesh is still there. I might want to tweak the mesh and update it, but it's all there for me. All I really need to do is change the analysis type. Again, it defaults to a linear static, so I can edit that, change it to a non-linear static, and when I say okay, when you change to different analysis types, you'll get different options that show up in the tree. And one that shows up for nonlinear static is a nonlinear setup. What this allows you to do is to capture intermittent moments of stress, if you will, or intermittent calculations, if you will. So I can say, well, let's grab 10 increments. You can plug in whatever number you want to here, but I would advise against doing something like that. The higher you go, the longer it's going to take that test to run. So I would start out probably 10, maybe go 20 and go from there. The other thing you need to do is also turn on intermittent output. This allows you to grab those intermittent calculations. What this actually does is it takes your load situation and breaks it up into however many increments. So in this case, it's going to take that load and break it up into 10 increments, and it'll run 10 individual tests. It allows me to go back and say, okay, test number 1 is 10% of my load. What's my stress look like for 10%? Test number 2 is 20%, 330, you get the idea. So you can kind of dial in if 100% of the load exceeds the yield strength of the material. So it fails at 100%. Where does it fail? We know it fails at 100. What about 70%? You can scroll back look at the 70% test and see what your stresses were. So when I invoke that option and I run the analysis, what you're going to see show up is that nonlinear status progress bar. And you're seeing each one of those increments, each one of those tests. So you're seeing that load situation at 10, 20, 30, 40, all the way up to 100%. And when the results are done, we'll be able to go back and dial in to see those intermittent outputs. So it defaults to a shell von Mises, so we can see the stresses on that. And you'll also notice up here at the top, it gives me a pull down to where I can say, okay, it's already showing me increment 10, so that's 100% of the load. But I can dial it back and say, okay, well, 50% of the load, what does that look like? And it dials in and shows me we're looking at about 49,000 PSI stress. Okay, what about 20% of the load? So that's what nonlinear brings to the table, is that intermittent output, plus some other bells and whistles, but that's huge. Because if you know running a linear that it fails at 100%, you can actually dial it in and find out where it fails. So looking at this, we had 10 inches of displacement in a linear test. Now I'm going to change this from a stress to a displacement plot. And instead of load 2 or increment number 2, I'll look at it, increment number 10, that's 100% load. On the linear static, it calculated 10 inches. But what we're actually seeing is about 4.3 inches. It's still a good amount, but I don't know that I would qualify that as a lot across 8 inches. I would expect that flat wall tank to have some movement, to have some flex. 4 inches, yeah, maybe, depends on the situation. You're going to know based on your products, your designs, and your criteria, whether this is good or bad. It's all going to be relative. With that, I'll go ahead and open it up for questions. Dan, how's the question and answer log looking?
All right, so I tried to answer some of them at the best of my abilities, but so there's a few good questions. One was asking about what happens if you don't select the total force, and that I believe is where if you select multiple faces, that it will apply that force across the total of those faces that are selected. Correct me if I'm wrong.
Yeah, each one of those faces gets that exact load. So if you put 100 pounds in there and you do not select total force, if you've got 10 faces selected, each face gets 100 pounds. So when you select total force, then that 100 pounds is broken up amongst those 10 faces. So in that scenario, it would be 10 pounds per face.
Perfect. Another one was, and it seems a lot of the questions kind of is talking about the conversion. So you really open up a can there. So one of them was asking, what's the, can we expand upon the importance of conversion? I know you mentioned that the importance of that is to get tangible results that match what you would expect in real life, right?
Right. The ultimate goal, again, is when you're starting out with Nastran or any other simulation product, when you're starting out running your first simulations, you want to get the software to match what you already see in the field. The reason for that is that lets you know you have all of your settings right, you have your material properties right. By the way, material properties is probably the biggest reason for analysis mismatches. And that can go back to take whatever materials you have out in the shop. Your supplier might have a material sheet on that, but what you're using may not exactly match the test bars that the supplier pulled that information from. So have the material you're using tested, and that'll give you dead on results of what you're using and what's at play. We've had a lot of customers go back to an independent lab, have that material tested, come back and say, that was it. Now our results are dead on, they're perfect. So that's a big hurdle to get over. The other thing is, once you get the analysis software tweaked to where it's predicting what you're seeing, The whole point of convergence is so that you can run multiple tests, refining the element count. The more elements you get, the more accurate your analysis is. The fewer elements, the less accurate. I could turn these meshes down to a very coarse number, and my stress calculations and deformations will be way off, grossly off, unbelievably off. At the same time, I could also go so super fine that I could start to see stresses in areas that really shouldn't have stress. And that's typically you're going to see that pretty quick. You're going to notice that. But if your mesh is too coarse, your numbers are off the same way. So you want to find that sweet spot. And once you start refining your mesh, what you're doing is you're building confidence that, okay, we're looking for the right one, we're looking for the right mesh size. Two, we're looking to make sure that just increasing or decreasing the element count has little to no effect on the results. You want to run multiple tests and see little to no change from test to test to test. That way, that's your proof. Go back to mathematics when we had proofs in college and high school. Hated proofs, but go back to that, and that's what the professor was doing. You worked out the equation, then you had to prove your answer. That's really what convergence about the mesh is doing. It's proving that you're on the right track because your test results aren't changing. Hopefully that helps.
Yeah. And there was another question that was kind of in that same ballpark. When you're doing the conversions and things like that, you were talking about the outlier. Is there a way to isolate that mesh node and suppress the outlier?
No, there's no way to isolate a particular node. For that matter, there's no good utility to find which node that is, because your von Mises is simply your averages of your first and third principles, right? So
Yep.
to go through there and probe each individual node, we've got better things to do. So it's usually easiest chart your results, and you're going to see that outlier test real quick. Chart not just the results, but what were your settings during that test? What was your global mesh, and were you using any local mesh control? Because that's really all that's changing. You're not changing your load, you're not changing your materials or your boundary conditions or your constraints, just refining that mesh. So you only got 2 or 3 pieces of information to chart. And when you see that outlier show up, go back to those settings and tweak them a little bit less, and see if it kind of pulls it back into play. 9 times out of 10, that's what will happen. There's even some cases where simply rerunning the test with the same results will give slightly different results. Again, it goes back to how each mesh element is calculated, and it's not in any particular order.
Understood. I know in this next question, I can answer this one. What is the best way to save the results? And the answer is to save your part, the assembly, because the environment that is running actually saves those results within its files. And so when you come back into that environment, you open up and review, it will actually show you the results of the prior runs that you've done.
And there's also a report option.
Yes.
Especially for linear static. The report option is not available on all of the Nastran tests, but definitely on linear static and a couple others. You can right-click on that right-click on that analysis, generate report, and it will give you material information. It will give you boundary conditions, the mesh settings, and then it will give you screenshots of each of the result plots. So that report you can generate as an HTML, PDF, and share it inside the company.
All right. So we got a couple of questions here. So if we miss some of the questions, not skip necessarily, but if we miss some of the questions, we will be getting back to you with an email to kind of answer some of the other ones. Welds. Okay. If I have a part with welds, is it okay to include them into simulation and try to refine the results? I will often see. Okay.
Having recently spoke with an actual weld engineer, his recommendation matches the recommendation we've been given for a number of years now. Do not include the welds. There's a lot of unknowns that come into a weld situation, And for one, even if you use Inventor's weldment environment and you build the welds into the model, when you take that into Nastran, those welds disappear.
Yes.
And if you try to manually model the weld bead, model the weld bead as an IPT, then you're getting into a very gray area of the contacts don't accurately reflect what's happening in the real world. So one option is go ahead and make your weldment, put your welds in there, and then simplify it out as a single piece part, because that does a couple of things. It assumes that your welds aren't going to fail. It also takes contacts out of the equation, which can, when you're working with a weld situation, you can get into some fuzzy gray area with contacts. That's also the recommendation from the Nastran folks at Autodesk, is to step it out or simplify it out as a single piece part. Also, the other recommendation is to just run the analysis on your assembly, no welds, set up your contacts, assuming bonded contacts and assuming the welds don't fail. That's the gray area. We know in certain situations the weld is going to be the first bit to fail. We also know in other situations the weld shouldn't fail, but there's a lot of things that go into that weld. Is it homogeneous with the materials that it's connected to? What's the grain structure? What's the penetration of that weld? So there's a lot of unknowns that go into that raise red flags when you're working with welds. No simple answer, I'm sorry.
Awesome. All right. Doesn't Nastran have the ability to automatically do a convergence study now?
There are automated convergence studies built into the software, and that is some of the convergence that happens within the tests, but not from test to test to test to test. So when you run one simulation, it's not giving you just one result. There's actually sub-tests that are happening inside that in the background. You don't actively see it. You see it when you see the nonlinear analysis, you see those tests run. But on something like a linear, you don't see it, it's hidden. And the convergence that's in there is giving you results based on those internal tests converging. You still need to run mesh refinements and run separate tests manually and plot out and chart those results.
Can nonlinear analysis determine the ultimate strength or just the yield point of material? Or of the design, I should say.
That's a bit of a loaded question, because all of this goes back to the material properties that are entered for the model. That's where it's all based off of. So if your material properties are off, your results are going to be off. Now, if you're trying to find, the optimal material to use, you can plug around and play with different materials and play with some of those values. That can help you optimize for the right material, say grade of material or something like that. You could do that. There's no automated tool in Nastran to do that I know of.
All right. Is using the convergence settings with the H refinement the same as manually charting the convergence?
No. The H refinement goes back to those individual tests that are happening as part of the one test. So the H refinement is happening behind the scenes.
Okay. And I think the final question I see here, you were logging in the results of your analysis with Excel manually, but does Nastran have a native way to track, reiterate the results within the FEA environment?
Not that I have found. I know that's been asked for, but I've not seen it been incorporated yet. I've looked around. It's been a couple of releases since I looked for it, but as far as I know, there's nothing there to automatically log those results and chart them.
I think that is all the question. There is one long question from Gary Moore. I think what we will want to do with this one is to meet with him or talk to him on the phone to get a better understanding of what he's asking. But it is, I think pretty much all the other questions are pretty much answered at this point.
All right. And like Dan said, if there's any other questions that either we didn't get to or that kind of filter in after we end the meeting, we'll definitely address those offline, and someone from Hagerman will get in contact with you to get clarification and hopefully get you the answers. So that being said, I appreciate everyone attending today's webinar. Thank you and have a great day.